Hello students, welcome back to session 12 of linear transformations. So in the last class you have studied what's meant by a trace of a matrix and in turn trace of a linear transformation, and also we have solved few examples related to finding the trace of a matrix or the trace of a transformation. Also studied a few results related to trace argument. Okay. So in this class, let us take up the transpose of a matrix. Okay. So if Aij belongs to Fi, means it's an n cross n matrix with a trace in the field F, then the transpose of A written by A prime or At. Okay. A prime or At is the matrix At is equal to Aj for each I and j. If A is Aij, then A transpose is Aj for each I and j. Or look here. So if T from V to U, is an arbitrary linear mapping, arbitrary linear transformation from a vector space V into a vector space U, then now for any linear function phi belongs to U star. What is U star? U star is the dual space of U, right? Any functional means it's a mapping from U to K. The function means the linear map from phi from U to K is called the linear function on U. So that belongs to U star. The composition phi of t is a linear mapping from where to where? It is a linear mapping from V into K. V into K means what? It's an element of V star. It's an element of V star. That is phi of t belongs to V star. That is, if t is a mapping from V to U and phi is a linear function on U, means phi is a mapping from U to K, then phi of t is a mapping from V to K. Phi is a mapping from V to K. Thus, the correspondence means the mapping which maps each phi to phi of t. Each phi to phi of t is a mapping from where to where? Phi belongs to U star. So it's a mapping from U star to V star. It is a mapping from U star into V star. We denote this by T. T means transpose of T, and call it the transpose of T, That is, Tt is a mapping from U star to V star defined by Tt of phi is nothing but phi of t. Tt of phi is nothing but phi of t. Thus, Tt of phi at the point V is phi of t at the point V. Okay, this holds for every vector V belongs to V. Clearly, the transpose mapping Tt as defined above is definitely linear. It's a linear mapping. For example, you consider this. Consider the following basis of R2. Okay, so these are the basis for the vector space R2, say 2, 1, 3, 1. Now we need to find the dual basis phi 1, phi 2 related to V1, V2. Okay, so let's find this now. So okay, we need to, yes, the dual basis means what? When you say, you already studied this in vector spaces. Okay, so when you say if V1, V2 are any two vectors, phi 1, phi 2 are called the dual basis to V1, V2. They are element of V star, means what will happen? Phi I of Vj is equal to S 0 if I is not equal to j, 1 if I is equal to j. Here phi I is nothing but Vi cap. Vi cap of Vj is nothing but 0 if I is equal to j and 1 if I is not equal to, if 1 is I is equal to j and 0 if I is not equal to j. These are already you studied. Okay, so now I take up S. So we need to find linear functionals. Phi 1 of xy is a of x plus b of y, a of x plus by, plus phi 2 of x comma y is cx plus dy, such that phi 1 of v1 is 1, phi 1 of v2 is 0, phi 2 of v1 is 0 and phi 2 of v2 is 1. Okay, now phi 1 of v1 means phi 1 of v1 is 2, 1. Phi 1 of 2, 1 means according to this as 2x plus y. 2, this is x is 1, x is 2, y is 1 means 2a plus b. 2a plus b, that will be equal to 1. So 2a plus b is equal to 1. Similarly, phi 1 of v2 is phi 1 of 3 1. 3 1 is 3a plus b, which is 0. So if you solve for these two equations for a and b, you get a is -1 and b is 3. Okay. And phi 2 of v1 is phi 2 of 2 1. Phi 2 of t1 is what? 2c plus d, that will be equal to 0. Phi 2 of v2 is 1. So phi 2 of 3 1, that is 3c plus d is equal to 1. So solving these two equations, we see that the value of c will be found to be 1 and d is found to be 2. Therefore, the dual basis is phi 1 of xy is equal to -x plus 3y. Phi 2 of xy is equal to x minus 2y are the linear functionals. Okay, are the linear functionals dual to the, or they are the dual basis to the basis elements v1 and v2. Okay. Now, let's take up this theorem. Look here. Suppose T is a linear transformations from V into the vector space V into the vector space U, and let A be the matrix representation of this transformation T related to the basis Vi of V and Ui of U. Then the transpose matrix AT is the matrix TT from where to where? U star to V star related to the basis dual to Ui and Vi. TT is, then the transpose of T is the matrix of the transformation TT from U star to V star related to the dual basis to Ui and Vi. Now we will prove this. Okay. For this, yes, you know that now T is a mapping from V to U with basis Ui and Vi. Means T of V1 can be written as T of V1 is an element of where? It is an element of U. So T of V1 can be written as a linear combination of basis elements of U. So therefore, I'll write T of V1 as A11 U1 plus A12 U2 etc. A1n UN. Next is T of V2 A21 U1 A22 U2 etc. A2n UN and so on. Similarly, T of Vn can be written as AM1 U1 AM2 U2 etc. AMn UN. Therefore, the matrix A will be, means the matrix of T will be A, that is A11 A12 etc. A1n A21 A22 etc. A2n and AM1 AM2 etc. AMn. Now we need to find the matrix of TT. So that is, we need to show that TT of sigma 1 is equal to what? TT of sigma 1 is equal to A11 phi 1 A21 phi 2 etc. AM1 phi m. This is very careful, indexing is very important. AM1 phi m and TT of phi 2 is equal to, TT of sigma 2 is equal to A21 phi 1 sorry A12 phi 1 A22 phi 2 etc. AM2 phi m and so on. TT of sigma n will be equal to A1n phi 1 A2n phi 2 etc. AMn phi m. So that if you take a matrix, this will be definitely the transpose of A. Okay, transpose of A. You call by this number 2, where sigma and phi j are the bases dual to the basis Ui and Vi respectively, where sigma and phi j are the basis dual to Ui and Vi respectively. Now let us take V belongs to V. Now if I take the element V belongs to V, then what will happen? Let's see. If I take V belongs to V, then V can be written as K1 V1, K2 V2 etc. Km Vm. There are m number of basis elements. So any element in V can be written as linear combination of basis elements. This implies T of V is equal to K1. Since T is a linear map, T of V is K1 into T of V1, k2 into t of v2 etc. km into t of vm. Now each of these t of v1, v2 etc. vm can be written as k1 into t of v1 is again it's an element of u, therefore it is a linear combination of basis elements of u. Therefore k1 into a11 u1, a12 u2 etc. a1n un. Next plus k2 into t of v2 can be written as a21 u1, a22 u2 etc. a2n un. And so on. The last element is km into am1 u1 plus am2 u2 etc. amn un. Okay. Now you take the coefficients of u1, you correct the coefficients of u1, u2 etc. up to un separately. You get, look here, k1 into a11 plus k2 into a21 etc. km into am1 u1 and so on. The last element is k1 into a1n plus k2 into a2n etc. km into amn into un. Or if you write in a summation notation, so this is equal to summation I is equal to 1 to n k1 into a1i plus k2 into a2i etc. km into ami into ui. So I takes the value from 1 to n. Hence for j is equal to 1 to n, tt of hence for j is equal to 1 to n, tt of sigma j of v is sigma j of, this can be written as sigma j of t of v. Sigma j of t of v now, just now we written, so this is the expression for t of v. So I written this as summation I is equal to 1 to n k1 a1i plus k2 a2i etc. km into ami into ui. Sigma j applies for this. This implies k1 into, look here, sigma, if you apply sigma j for, so up to uj, sigma j of uj is 1, for all other terms it will be 0. So this becomes k1 into a1j plus k2 into a2j etc. km into amj. For other terms it will be 0 because sigma j is the dual basis to uj, right? Or sigmas are dual to ui's. So you call by this number 3. So on the other hand, for j is equal to 1 to n, on the other hand, for j is equal to 1 to n, say a1j phi 1 plus a2j phi 2 etc. amj phi m of v can be written as a1j phi 1 plus a2j phi 2 etc. amj phi m of v means k1 v1 plus k2 v2 etc. km vm. You apply again, phi a of vi is, phi a of vj is 0 if I is not equal to j and 1 if I is equal to j. Accordingly this becomes k1 into k1 into a1j plus k2 into a2j etc. km into amj. Okay, so we call by this number 4. Now from 3 and 4 you can see that tt of sigma j of sigma j of v is equal to a1j phi 1, a2j phi 2 etc. amj phi m of v. Now this v is taken to be arbitrary. Therefore tt of sigma j is a1j phi 1, a2j phi 2 etc. amj phi m, where j runs over 1 to n, which is nothing but what? These are the system 2. Okay, these are the system of equations 2. Therefore we have proved the required result. Means we have find out the matrix of tt. Tt is the transpose of t. Okay. Now say look at this small result. Say for all AB belongs to Fn, for all n class n matrices over F, transpose A transpose whole transpose is A itself. A plus B whole transpose is A transpose plus B transpose, and AB transpose is B transpose into A transpose. These are the element results that you have studied in your lower classes. Okay. Note that AKT is AT power of k for all positive integers k, means the transpose of A power of k is A transpose to the power k. Okay. Now when A is invertible, A inverse of a transpose of a inverse of a matrix is the inverse of a transpose of a matrix. A inverse over transpose is A transpose inverse. These are elementary results. I left the proof to you only. Okay. Yes. Next is, look here. So the matrix A is said to be symmetric matrix. When you say the A is said to be symmetric matrix, if A is equal to its transpose or A transpose is same as A and is said to be skew symmetric matrix if A transpose is same as minus A. Okay, A transpose is equal to A means symmetric, A transpose is equal to minus A means skew symmetric. Now look here, if characteristic of F is 2 means characteristic of field is 2, then 1 plus 1 is 2, 1 plus 1 is 2, 2 is equal to 0 means 1 plus 1 is equal to 0 means 1 will be equal to minus 1. Okay, 1 will be equal to minus 1. So we cannot able to distinguish between skew symmetric and symmetric matrices in the field of characteristic 2. So we make a flat assumption that the characteristic of F is different from 2. Okay, now ready ways of producing symmetric and skew symmetric matrices are as follows. Suppose you are given some matrix, how to make them, how to obtain a symmetric and skew symmetric matrix from that. So this is the procedure. If A is an arbitrary matrix, then A plus A transpose is always symmetric and A minus A transpose is always skew symmetric. So if you given a matrix A, then A plus A transpose is symmetric and A minus A transpose is always skew symmetric, and the matrix A always been the sum of A plus A transpose by 2 plus A minus A transpose by 2, means it can be written as sum of symmetric and skew symmetric matrix. Another method for producing symmetric matrices is as follows. If A is an arbitrary matrix, then both A into A transpose and A transpose into A are always symmetric matrix. Okay, understand this? So if A is an arbitrary matrix, then A into A transpose and A transpose into A are always symmetric matrix. Okay, so this is the procedure for obtaining symmetric and skew symmetric matrices. So that's all for this class. Thank you very much for listening.